Large language models rely on millions of high-dimensional vectors to recall information. Every time you submit a prompt, that text is translated into a single query vector dropped into this mathematical space. The core task is to find the specific vectors in the database that are mathematically closest to that incoming query. This diagram represents the exact k-nearest neighbor, or KNN, approach. To guarantee the closest matches, the algorithm calculates the precise distance between the query and every single vector in the system. Looking at this overlay, we see the time complexity of this operation is O of n. As the database grows, the time required to search it scales perfectly linearly. Calculating millions of exact distances per query requires massive compute power. In real-time applications where users expect instant results, this latency destroys the user experience. Achieving scale in AI retrieval requires moving away from the requirement for perfect mathematical exactness in favor of speed. This is the role of approximate nearest neighbor, or ANN, algorithms. The trade-off is clear. By intentionally sacrificing a minute fraction of absolute accuracy, the system achieves exponential gains in retrieval speed. The industry-standard algorithm for managing this trade-off is Hierarchical Navigable Small Worlds, or HNSW. HNSW is a hybrid architecture built from two distinct foundational data structures. The first component is the navigable small world, which is a specific type of spatial graph. The second is the skip list, a probabilistic method for bypassing data. To understand how HNSW can search 1 billion vectors in milliseconds, we must build it from scratch by combining these two structures. The navigable small world, or NSW, represents vectors as nodes on a graph. Edges only connect vectors that are mathematically highly similar to one another, resulting in a localized web of connections. To search this graph, the algorithm uses a mechanism called greedy routing. In greedy routing, the algorithm evaluates the neighbors of the current node and always jumps to the one mathematically closer to the target query. The flaw in flat architecture is the high degree of separation. Navigating massive datasets requires too many small jumps. This leads to the local minimum trap. If a search enters a cluster where no edges point closer to the target, it dead ends prematurely. This makes a flat proximity graph unreliable at scale. Greedy routing gets stuck in dead-end neighborhoods. To solve this, we move from graphs to a one-dimensional computer structure, the sorted linked list. Finding a specific number in a standard linked list requires a linear one-by-one traversal. The skip list is an upgraded architecture designed to bypass that sequential checking. It generates upper layers by probabilistically selecting a fraction of the nodes from the layer below. A search begins on the highest, sparsest layer, taking massive structural leaps across the data. If the search overshoots the target, it drops down to a denser layer to refine its position. Skip lists convert slow traversal into logarithmic O of log n speed by building macro highways over the microdata. The goal is applying this vertical layering to the complex reckoning of a navigable small world. We start with base layer 0, which contains the complete proximity graph of every vector in the database. To create layer 1, the algorithm probabilistically selects a small percentage of nodes from the base layer to promote upward. Because there are fewer nodes here, the connections between them stretch across vastly larger distances in the vector space. This stacking continues, with each new layer containing a fraction of the nodes from the layer below. This process repeats until reaching a top layer that contains only a handful of entry points connected by space-spanning edges. This structure resolves the local minimum trap by ensuring alternative routes always exist on higher planes. This is essentially a multi-dimensional skip list, stacking proximity graphs to bridge the entirety of the vector space. A search always initiates on the highest, most sparsely populated layer, where long edges allow the algorithm to instantly cross the graph. The algorithm conducts greedy routing until it hits a local minimum on that layer. Instead of failing like a flat graph, the algorithm drops vertically to the same node on the denser layer below, where a new set of local edges becomes available. The search zeroes in, moving from macro navigation down to micro precision through each successive layer. The final resolution occurs on base layer 0, where the algorithm identifies the nearest neighbors within that localized neighborhood. The upper layers ensure the algorithm bypasses the vast majority of the database, focusing mathematical comparisons only on the most relevant vectors. We can now compare the mathematical reality of these two approaches. Exact KNN search guarantees a 100% accurate result, but it requires crippling O of n compute time. By sacrificing a minuscule percentage of accuracy, HNSW flattens the compute curve to O of log n. Logarithmic scaling means that doubling the size of a database only adds a fraction of a millisecond to the query time. Instant contextual recall for large language models relies entirely on this engineering achievement. By combining the micro-routing of small world networks with the macro-skipping of linked lists, HNSW solves the latency bottleneck of high-dimensional space.